All right, so we have talked about our ideal gases. When we have an ideal gas, we can use the equation PV equals nRT, right? But this is for when we only have one type of gas. But sometimes we have multiple types of gases in the same sample. So when we have multiple types of gases, we have to use the law with partial pressures, where our pressure total, P total, is equal to pressure 1 plus pressure 2 plus pressure 3, all the way down until we get all of our pressures in there, okay? So an example of this is oftentimes we will collect gas over water, right? So we'll have some water in a tube in there, right? And we're going to be collecting a gas, right, that's coming through this tube this way, okay? So we'll collect the gas as it displaces this water. So as we collect that gas, we have the gas that's getting pushed in here, right? Maybe that's that amount there. But we also get the vapor pressure from the water, okay? So we have two different pressures here, right? We are going to have the total pressure, right? That would be like our atmospheric pressure. We're going to have a vapor pressure from the water, and then we'll have the pressure from the gas that we are putting in there, okay? Fortunately, oftentimes our pressure for water, right? Pressure for water is generally known, okay? It kind of depends on our temperature. So P water is a known value, okay? So if we have the total pressure, right, and we know the pressure of water, we can subtract the pressure of water from the pressure total, and that's going to give us the pressure of the unknown, okay? So we always just have to remember, right, our pressures are going to add together to get to the total pressure, okay? So another example of this is when, right, if we had something like oxygen being in air, and its partial or its mole fraction would be 0. Whoops, here we go, 0.2095, right? So this is the mole fraction, right? So I have 20.95% of my air is oxygen. What pressure is coming from that oxygen? All I would have to do is say, okay, well, it's 0.2095 times my pressure. So say my pressure is 735 millimeters of mercury, and that's going to be equal to 154 millimeters of mercury. Okay, so if we have a percentage, right, a mole fraction, right, then we can just multiply it to get the partial percent. The other amount, right, we would have, I don't know, 600, 580, roughly, 580 millimeters of mercury that's coming from my other elements or other gases that were in air. Okay, so our kinetic molecular theory of gases. So really, what we have said is that our particles, right, they're racing around, they're going wherever they want to go, right? They're moving all over the place. Oftentimes, right, our pressure is related to them kind of hitting the outside. So what we want to be able to describe is how fast are these molecules really moving. And turns out that our temperature is an average. Okay? So temperature is really a representation of the average speed of our particles. Okay? Right? Temperature is a measure of the kinetic energy. Right? Temperature is a measure of the kinetic energy, but it's an average kinetic energy of our particles. Okay? So our kinetic energy can also be described by the equation 1/2 mv squared, where m is the mass of my particle and v is the velocity at which it's moving, okay? So if we think about this, right, we have an average speed of our particles. We're going to have something that kind of looks like this, where this is just our number of particles, right? And this is the kinetic energy, the speed at which they're moving, right? So I could also say, really, it's the velocity. Most of them, right, are kind of right around this number, but there's going to be some particles that are moving at a higher speed. So as I increase the temperature, right, I'm going to increase the average kinetic energy, okay? So now my graph would maybe look something like this, where my hump, right, more of my particles have been moved past that point. Now my average is out here, okay? So my average speed is further out, right? So my velocity is going to be higher, okay? So this is my kinetic energy, my average kinetic energy is over further, okay? So I realized here these two need to be flipped, right? This should be my number of particles, and this down here should be my velocity, okay? So we're going to cross that out, and we're going to make that correction, okay? Right, so my average velocity here, right, has moved higher, so my number of particles, I have more particles that are moving at higher speeds. All right, so we can also use this to compare different particles. We know, right, that it also depends on the mass. So if I have different masses of my gases, then their kinetic energies are going to be maybe the same. The average kinetic energy will be the same, but they're going to be moving at different speeds. So I can compare hydrogen versus helium. Hydrogen, right, would have a mass of 1, so 1 AMU. My helium, right, would have a mass of 4 AMU. So my hydrogen, to have the same kinetic energy, my hydrogen, right, if I put this in here, same kinetic energy, say it's equal to 1 equals 1/2 times 1 times v squared. For me to get up to 1, right, I need my v squared to be equal to 2 there. But if I have helium, right, an average kinetic energy of 1, I have 1/2 times 4. Now my velocity, my v squared, this is now 1/4 of it, okay? So my helium particles, they are not moving at the same speed as my hydrogen particles, right? My hydrogen has to be moving much faster to have the same kinetic energy, okay? So if we remember our physics, right, we have velocity and mass, right, related to our kinetic energy, okay? So we can use this equation to then relate our actual speeds, okay? The last piece with this is our deviations from ideal behavior, okay? So we've said that our gases generally behave as ideal gases. And the reason being, right, that our particles are very far apart. So I'll say ideal particles. Our ideal particles are far apart, so they are not being affected by each other, essentially. We have deviations from ideal behavior, or we have real gases, when we basically either bring the particles really close together, or we do something and that now they aren't, the differences in them start to matter. So we either make our volume really very small, so our particles are close together. So real gases, particles close together. How would I do that? Right? I would do that when I maybe bring the pressure really high, or I make the volume really small, and I force our particles to be really close together. We are getting closer to a liquid. Right? In our liquid, our particles are closer together. Okay? So our real gases, oftentimes we force those particles closer together, and now they don't behave as an ideal gas because the particles may be just closer together. They're more similar to a liquid. We also are going to get real gases when we have intermolecular forces that come into play, right? Some gases, when they hit another gas particle, it's got that really sticky, really movable gas or electron cloud, right? That means that it's not going to bounce off as ideally, right? It's not going to bounce off the wall of our container really easily. So if we have intermolecular forces that are changing our gases, that's going to change away from our ideal behavior, okay? All right,